Hello and welcome everyone. So as we have understood in the vibration analysis, we have four steps. First one is the mathematical modeling, and that we have understood. Second stage is the formulation of governing equations of motions. So this is very important after mathematically modeling the vibrating system. So what is this equation of motion? Equation of motion are the governing differential equations, those equations which are governing the motion. Okay, so those governing differential equations describing the motion is known as the equation of motion. So why this is said to be differential equation? Because these equations involves the use of differential terms, okay, like d2x upon dt square and dx upon dt besides x and y, etc. Okay, so we go for higher differential terms also. So there are different methods, and out of them these five methods are most important, and these important methods are listed here through which we can derive the equation of motions. And out of all these five methods, I hope you all must have studied these three methods. First method is the simple harmonic motion method in your physics. Similarly, you must have studied Newton's second law of motion method in mechanics. And similarly, you must have studied conservation of energy method. So these three methods you must have done earlier, and we will be using these methods in formulation of equation of motion in vibration also. And these two methods, Rayleigh's methods and Alembert's method, are also not much different than the earlier three methods. We will be arriving to the similar equation of motion through all of these five methods. See, which method we have to apply in a given situation depends on the intuition of the person, or the experience, or the amount of practice that he has done. Okay, so let us begin with the first method, that is simple harmonic motion. And we have done a discussion on this topic, simple harmonic motion, and you can watch that video also. In simple harmonic motion, what is the most important criteria? There are two important criteria. One is that the acceleration is always proportional to the distance of the particle from its mean position. And second point is that this is always directed towards that mean position. Okay, only then we can say the particle is undergoing SHM, simple harmonic motion. So this is a very simplest form of periodic motion, and the basic concept, as we have said, that in this case we can write that acceleration is directly proportional to displacement. Acceleration, as you know, be represented by x double dot, and it is proportional to the displacement x. Now this acceleration is also directed towards the mean position or opposite to the motion, so it is given a negative sign here. Okay, so here x is the rectilinear displacement, and you all know that dx upon dt is equal to x dot. Okay, so this is the standard notation here, x dot, and this is the velocity of the particle. Similarly, d2x upon dt square is the acceleration, and this is represented by x double dot. Okay, so this is the acceleration of motion, and here minus negative sign in this equation 2.3 indicates the direction of motion of a particle toward a fixed point. And what is that fixed point? Equilibrium position. Okay, and this is opposite to the direction of motion, as I have said. If the motion is going towards the left, the force applied on it will be towards right, and vice versa. So here we take the constant of proportionality is equal to k is equal to, here the k is equal to constant of proportionality is equal to omega n square. Okay, so this is also very important to be remembered by all of you, that k, constant of proportionality, will be equal to omega n square, and omega n, let us say it's a unknown parameter, we don't know much, but we can guess that this omega n is the natural frequency. Okay, And after rewriting equation 2.3 here as x double dot is equal to minus omega n square x. So taking everything on the left hand side, we can write this equation of motion like this, and we can see this is a second order linear differential equation. Okay, second order. Why? Because it is involving a term of d2x upon dt square. Okay, here there are terms which are having higher order differential terms of the variable x. Okay, so this is a second order linear differential equation, and the constant omega n is yet to be determined by the analysis, and we can find omega n. But after, in the third step, that we will discuss how we find the solution. Okay, so currently we are now focusing only on how to formulate the equation of motion. After learning all the 5 methods of formulation of equation of motion, we will go to the methods of solution of these equations. Okay, so let us see the second method, and that is the Newton's second law of motion. So this is a popular method, nothing to explain much, and the equation of motion is just another form of Newton's second law of motion, which states that the rate of change of momentum is proportional to the impressed forces and takes place in the direction in which the force is acting. Okay, so here we are considering a spring. You are seeing this spring here, and this spring is hanging from the wall, and this is the spring constant K. Okay, and this is the unsupported length of the spring from here to here. All right, so here now we are going to load this spring with a mass block of mass m. Okay, so this spring is assumed to move only along the vertical direction, so it is having only 1 degree of freedom in the y direction, and let us take the x-axis towards this direction. Okay, and y-axis we can take accordingly like this. All right, so this spring has got spring constant K, and the mass of the spring is negligible. Okay, so here if we apply the mass block of mass m here on this spring, then the mass m will take the spring down by certain amount of static deflection represented here by delta. Okay, and this delta can be found out by this equation. Okay, how it is? Because the weight will be equal to, weight is equal to mg, and mg is acting downwards. Okay, so spring will now apply a force K times delta. Okay, so K delta will be equal to weight of the block. Okay, and this delta is the static displacement, and it can be obtained as W upon K. Okay, so this is how we can find the equilibrium position of the block after hanging it from the spring. Okay, so after hanging the mass, it will go certain amount of static displacement, and it will remain in equilibrium there, and the mass will remain static at that position. But what happens if we take the mass still more distance from its equilibrium position? Now this is static equilibrium position. Okay, and if we stretch the mass or give an initial displacement by x, then what will happen to this mass? And if the spring is only assumed to move in the vertical direction, then the spring mass system will start oscillating it to and fro in vertical direction. Okay, so when the load W is pulled down by a little, by some force initially, and then the pulling force is removed, so then the load W will continue to execute vibrations up and down, which is called free vibration, because we have removed the initial load that we have applied initially at time t equal to 0. So here Ft is equal to 0 later on, so it's a free vibration. And now the restoring force, because we have stretched the spring now extra. Okay, now spring displacement is delta plus x. Okay, and this is the mass hanging from the spring. All right, now the force that is being applied from this spring will be represented by Fs, and the weight of the mass here is W is equal to mg, or you can write like that. Okay, so weight is being applied in the downward direction. So now the restoring force in x direction is the vertical direction, will be equal to W minus k times delta plus x, because delta was the static displacement and we have even more displaced it from the static position by amount x. So W minus k into delta plus x. Okay, so this is completely taken. Now if we write the restoring force, it will come out to be equal to W minus k delta minus kx, and W was equal to k delta. Okay, so k delta minus k delta will get cancelled, and restoring force F will be equal to minus kx. And from Newton's law we can write force as m into acceleration. Force is equal to mass into acceleration. Acceleration is represented by mx double dot. So mx double dot will come out to be equal to minus kx. Okay, taking everything on the left hand side, we come to this equation. Okay, finally this is our equation after dividing it by m on both sides. Now if we compare this equation that we have obtained from the Newton's second law and it compare it with the previous one, SHM equation, then we can see that omega n square, which we took as an constant of proportionality there, is coming out to be equal to k upon m. Okay, so we can say that omega n is equal to root under k upon m. Okay, and of course here k is the spring constant in the unit Newton per meter, and mass is the mass of the block. Okay, inherent property. So k is inherent property of a spring, mass is the inherent property of the inertia property of the block. So omega n will also be an inherent property of the mass block system, spring mass system. Okay, so omega n is here said to be the natural frequency. Okay, natural frequency is very important to calculate, and natural frequency is also known as angular velocity. Okay, so unit is in radian per second. Okay, all right, so this is how omega n is calculated. So all of you can remember this formula, omega n is equal to root under k by m. This is an important conclusion that we derive here. Now the third method, see, now you must have seen that from all the methods we are coming to the same conclusion. So similarly, if we use energy method, and we all know the conservation of energy, and since we are studying what, undamped free vibration right now, so there is no as such friction, so there is no loss of energy. Okay, so in that system, total energy of the system is equal to potential energy plus kinetic energy. Okay, the total energy of system is partly potential and partly kinetic. Okay, and according to the law of conservation of energy, total energy remains constant. So kinetic energy plus potential energy remains constant. And if we differentiate this equation here, then we will differentiate, and the constant will be differentiated as 0 here. Okay, because differentiation of a constant is 0. So after differentiating this equation, we arrive to this. First of all, let us differentiate kinetic energy and potential energy separately. And we know kinetic energy is what, half mv square, and mv, so v, velocity, is represented here as x dot. You see it here, x dot. Kinetic energy is half m x dot square. Similarly, potential energy in the spring, potential energy is stored in the spring, is equal to half kx square. I hope you know this. So after taking differentiation in this equation, d upon dt of half mx square x dot square plus half kx square. Now in this equation we have to do chain substitution method. Now first of all half m is constant, it has come here. Then x dot square will be differentiated as 2x dot, okay, and then we have to do again a differentiation of x dot. So 2x dot is multiplied here, x dot का differentiation क्या होगा, x डबल डॉट, समझ रहे हैं? तो ये समझना होगा, ये differentiation हाफ m, ये तो कांस्टेंट था, ये बाहर आ गया. उसके बाद फिर हमने 2x डॉट आएगा डिफ्रेंसिएशन में, ठीक है. फिर x डॉट का भी डिफ्रेंसिएशन मल्टीप्लाई हो जाएगा, जो हो जाएगा x डबल डॉट, ठीक है. ये बहुत ही आसान है. सिमिलरली अगर पोटेंशियल एनर्जी को डिफ्रेंशिएट करें तो हाफ k तो कांस्टेंट है, ठीक है, और x स्क्वायर का डिफ्रेंसिएशन होता है 2x, ठीक है. x स्क्वायर को डिफ्रेंशिएट कर दिया, अब हमें x का डिफ्रेंशिएट करना है, तो x का डिफ्रेंशिएशन क्या होता है, x डॉट होता है, ठीक है. नाउ आफ्टर राइटिंग दिस इक्वेशन everything on the left hand side, so now we have to see what is common in both equation. I think x dot is the common in both the terms, so x dot is taken and it got divided in the right hand side. So finally equation comes out to be mx double dot, with this two get cancelled, this two gets cancelled, mx double dot plus kx equal to 0. So we can see from all the methods we are arriving to the same equation again and again, okay. This is the simple equation of motion all the time, in especially in case of undamped free vibration, okay. Now let us come to the Rayleigh's method, and in this method it is assumed that the maximum kinetic energy कब होती है, जैसे पेंडुलम है, तो पेंडुलम जब इस तरीके से ऑस्किलेट कर रहा होता है, तो आप बताओ मैक्सिमम काइनेटिक एनर्जी कहाँ पे होगी, बॉटम में, है ना, क्योंकि ये जैसे ही एक्सट्रीम पोजीशन पे जाएगी इस समय इसकी काइनेटिक एनर्जी 0 हो जाएगी, ठीक है. एक्सट्रीम पे क्या ज़्यादा होती है, पोटेंशियल एनर्जी, और मीन पोजीशन पे क्या ज़्यादा होती है, काइनेटिक एनर्जी, ओके, दैट्स क्लियर. So it is assumed that the maximum kinetic energy is at the equilibrium position and it is equal to the maximum potential energy at the extreme position, ठीक है. ऐसा एज्यूम किया जाता है रेले मेथड में कि के ई जो मैक्सिमम है, कहाँ पे मैक्सिमम होगी, एट इक्विलिब्रियम पोजीशन, ओके, एंड इट विल बी इक्वल टू, किसके इक्वल होगा, पोटेंशियल एनर्जी की मैक्सिमम वैल्यू पे. मैक्सिमम वैल्यू कहाँ पे होगी, दैट विल बी ऑन एक्सट्रीम, ऑल राइट. सो दिस इज सिंपल कॉन्सेप्ट बिहाइंड Rayleigh's मेथड, एंड द मोशन इफ बी एज्यूम टू बी SHM, इट इज रिप्रेजेंटेड एज x इज इक्वल टू a साइन ओमेगा एन टी, ठीक है. ये रिप्रेजेंटेशन होता है SHM मोशन का, साइनोसॉइडल रिप्रेजेंटेशन है, जहाँ पे a what is x is the displacement of the system from its mean position at any time t, and a is the maximum displacement of the system from its equilibrium position to the extreme position. तो a को क्या कहते हैं, एम्पलीट्यूड, ठीक है. मीन पोजीशन से एक्सट्रीम पोजीशन के डिस्टेंस को क्या कहते हैं, डिस्प्लेसमेंट को एम्पलीट्यूड. सो वी कैन से दैट द मैक्सिमम वैल्यू ऑफ x क्या होगी, x मैक्सिमम क्या होगा, x मैक्सिमम विल बी a, ठीक है, ये तो क्लियर है. सो इफ वी डिफरेंशिएट द इक्वेशन x इज इक्वल टू a साइन ओमेगा एन t, what will be the differentiation? Differentiation will be written as x dot will be equal to a sin omega, a is the constant, so it will not be differentiated. Now sin omega and t will be differentiated as cos omega and t, and now we have to again differentiate omega and t. So omega and is constant, it will come here, and t is differentiated with delta t, it is 1. So this is my final equation, a omega n cos omega n t for velocity, okay. So the same thing is written here. So from this we can get the maximum value of velocity x dot, x maximum तो पता चल गया a होगा, ठीक है. a कब होगा, जब sin ओमेगा एन टी 1 हो जाए, ठीक है, ये वैल्यू जब 1 हो जाए तब x मैक्सिमम हो जाएगा 1. सिमिलरली अगर x डॉट मैक्सिमम कब होगा, जब ये cos ओमेगा एन टी ये वाली वैल्यू जब 1 हो जाए तो x डॉट मैक्सिमम क्या होगी, a ओमेगा एन और ओमेगा एन है, ठीक है। सो नाउ वी कैन कैलकुलेट मैक्सिमम काइनेटिक एनर्जी एट द इक्विलिब्रियम पोजीशन विल बी इक्वल टू काइनेटिक एनर्जी क्या होगी, हाफ एम बी स्क्वायर हाफ एम एक्स डॉट स्क्वायर। एक्स डॉट क्या है, अभी देखा हमने, एक्स डॉट मैक्सिमम क्या है, a ओमेगा एन। सो आफ्टर यूजिंग हेयर we come to this value of Ke maximum. Now let us calculate the maximum potential energy at extreme position. It is equal to half kx square और x की मैक्सिमम वैल्यू क्या होगी, एम्पलीट्यूड के बराबर a के बराबर, तो पोटेंशियल एनर्जी मैक्सिमम ये हो गया। फ्रॉम रेले मेथड वी से दैट ke maximum is equal to pe maximum. So after equating both of these terms we come to this here you are now seeing this equity term, and we can cancel half and then what we arrive to, a square is also cancelled here. Now we can arrive to the equation that omega n square is equal to k upon m. So again we are arriving to the same equation once again. So omega n here is the natural frequency of the system. Now let us come to the fifth method, that is known as D'Alembert's principle. And this is a principle in which we use imaginary forces, okay, imaginary forces. So here we use the method of statics by applying imaginary forces. And what are those imaginary forces? Generally they are minus ma. I will tell you this in detail. So this method gives the solution of a dynamic problem, okay, by using the method of statics. See, there is a statics, there is dynamics, and what we are studying right now, dynamics. We are not studying statics. But this principle allows to make a dynamic system static, and then we can do the rest thing. Okay, so how a dynamic system can be made static? By applying some imaginary forces. ठीक है. So according to Newton's law, we know that force is equal to mass into acceleration, and then we can write this equation as F minus ma is equal to 0. Okay. So the D'Alembert's principle also uses the same concept here, that if a system may be in dynamic equilibrium, static equilibrium नहीं है, dynamic equilibrium, by adding to the external forces, अगर हम external forces में एक add करें कुछ imaginary forces, and that imaginary forces is equal to minus ma, okay, which is commonly known as inertia forces. Okay, imaginary forces को inertia forces कहते हैं, ठीक है. So why this minus sign? I will explain you. So here we apply an imaginary force ma. अगर हम ma amount का, a is the acceleration, and it is can be written as x double dot here, no problem at all. So if we apply ma in the direction opposite to the acceleration, ठीक है, that's why I am saying minus sign here, minus ma. So if we apply that amount of imaginary force on a dynamic system, then the system could be in equilibrium, and that equilibrium is dynamic equilibrium. So according to this principle, the transformation of a problem in dynamics may be reduced to one in statics. Now here is a spring mass system, and there is no damping at all in this case. And if we apply a force, let us say some force was applied and it has to go under some displacement x. So the force in the spring will be equal to kx, and this block is undergoing some acceleration in this direction a. Okay, now we have to apply on this block some imaginary force mx double dot here in the opposite direction of the acceleration. Okay, so when we have applied this imaginary force on this block, then this block comes into dynamic equilibrium. So using this D'Alembert's principles, we bring the body to a dynamic equilibrium position, and the inertia force mx double dot is to be added in the direction opposite to the direction of motion. Okay, so in this situation of dynamic equilibrium, if we write the equilibrium equation in x direction, it will be written as minus mx double dot minus kx will be equal to 0. So after arriving to this same equation once again and again, x double dot plus k upon m into x equal to 0. So again and again you are seeing here that we are arriving to the same equation of omega, and natural frequency is coming same in all the situations, and the equations are also similar. So this is how we do the formulation of equation of motions using different methods available to us depending on the intuition. So we will be discussing how to solve these equation of motions through different methods, and that we will do in the next videos. Till that, stay tuned and stay safe. Thank you.